I just began the recording, and yeah, so I'm super excited to talk about the frontier of like high energy physics. Um, so really, what I'm going to be discussing today is the experimental sensitivities in like the next generation beyond the standard model of physics. This is like, think of this as an experimental physics kind of presentation for mathematics people, or for people like more of an interdisciplinary mathematics and physics kind of audience. So that'll be the main target that I'm trying to accomplish today with this little presentation. But so we've entered this really decisive era in physics. We're transitioning from this definitive validation of the standard model. We're not really trying to validate the standard model anymore. Now we're trying to do a systematic investigation of the structural failures of the standard model of physics. So while it remains this triumph of 20th century physics, now it's very clearly understood as an incomplete framework that fails to account for most of the fundamental features of our universe. It's just a failing model in general. So, from the origin of mass to the nature of like cosmic expansion, there's a lot of interesting high sensitivity experimental programs that are they're no longer these complementary types of things, but we're trying to create a viable path for resolving current theoretical impasses from breaking this existing program. So the whole idea that I'm trying to lay before you with this Jet Space Institute little roadmap that will proceed is to evaluate this experimental landscape across and give mathematical kind of meaning, if you will, or give some just a slice of physical meaning to the mathematicians, and then vice versa. I'll be explaining both things, but the subject of neutrinos, dark matter, axions, and cosmic expansion. These are the four things. So these are very exciting topics. And the primary mission would be to be focused on these strategic objectives in the 21st century experiments that we'll go over today, is uncovering the origin of neutrino mass itself. So we need to establish what is the fundamental nature of the neutrino and its lepton number violation. We want to decipher the nature of dark matter through directly detecting it at these very unprecedented sensitivities that have taken years and years and years of engineering. So it's massive feat and accomplishment of experimental physicists. And a lot of technologies have come out of this, like radio pure germanium detectors and everything. So also we want to resolve the Hubble tension. So this is a discrepancy that signals the potential breakdown of our lambda CDM cosmological model. So really, this research is going to basically take the mathematics and physics boundaries of the standard model, clearly define what does it mean for something to be standard model, find the boundary of that, and then show where it ceases to be predictive and require, and predictive in its very statistical sense. This is what physicists have adopted to describe reality, is with Bayesian and fundamentalist statistics, which might be a fun fact for you guys. But we want to navigate this transition into physics beyond the standard model. Okay, so we have to be very clear with what the boundaries of the standard model are, and so we need to have a naming convention for physical observables and a rigorous consistency condition for the underlying theory of the standard model. We have to understand why the standard model is incomplete. It's because of these would be like symmetry breaking and boundary identification types of arguments. The nature of the neutrino mass, there's something called a Weinberg dimension 5 operator and Majorana mass terms. Neutrinos double beta decay. These are neutrinos double beta decay half-life measurements, and we'll get into what that is. Legend, Nexo, and Cupid are using specific isotopes. So germanium-76 is for Legend, which is one of the ones that I worked on. Xenon 136 and molybdenum 100 isotopes are the ones that we're probing for, whether they're nuclear voltaic probes or something like that. Or whether they're in liquid kind of these quantum liquids. Also, strong charge parity violation, CP violation is charge parity violation, and the axion. These are very interesting mathematically. I don't know if you guys have heard of like axial vectors and stuff like that, but it's very similar to that. The direct detection, what could break the standard model is direct detection of weakly interacting nucleon scattering cross sections in liquid argon measurements of charge parity violation and ordering at Dune, the Dune experiment. Topology, grand unified theories, spectral geometry. These all give us these global anomalies and unified gauge structures to play with. And so there's a lot of mathematical progress that could be done in these things as well for fundamental physics. And then lastly, the Hubble tension. So early versus late universe type of expansion rates. So by these are all points of failure of the standard model. And we wanted to find the parameters of the effective theory limit, quotation mark effective theory, of the standard model leading to these breakdowns of physical boundaries. So let's define the boundaries of the standard model. And my differential, you really need differential geometry to even begin talking about the standard model in a modern sense, in this 21st century kind of sense. It is basically defined on a principal bundle. You have SU3, which corresponds to chromodynamics, SU2 cross SU1, which corresponds to electroweak kind of dynamics, and there's 3 generations of matter and all this stuff. But we have to treat it as an effective field theory. So it's a low energy approximation of a more fundamental description of reality. So there's strategic kind of prioritization of experimental funding that requires everybody to focus exclusively on the areas where the standard model is demonstrably silent. So neutrino masses. The standard model lacks a mechanism for neutrino mass or lepton number violation, period. So that's the first failure of the standard model. The second is there's an observed asymmetry or imbalance between matter and antimatter that is unexplained. And also 95% of the universe's energy density is unaccounted for by the standard model. So that's dark matter and dark energy. There's something called the strong charge parity problem, where something called CP invariance in the strong interaction is fine-tuned to an effective degree. And how long is this going to be, really? The gauge hierarchy and gravity. So sorry, it's just going to go on as long as it's going to go on. I don't know how to answer that. The standard model it lacks a non-renormalizable quantum geometry for gravity. Yeah, sorry, I can't give you a straight answer. And then also the Hubble tension is a persistent greater than 5 sigma discrepancy in the expansion rate of the universe. So these are all gaps, right, in the standard model, and are essentially grounded in experimental. Don't switch. Sorry, I cut out. They're grounded in the experimental constraints, right? And this forces the fine-tuning of the strong charge parity problem, which is immediately this laboratory kind of smoking gun for the breakdown of the standard model group and neutrino mass with the Weinberg operator. So let's go straight to the Weinberg operator itself. The strategic importance of it, cannot be overstated. Everybody should be familiar with what the Weinberg operator is if you've really studied quantum field theory and its importance in fundamental relevance in today's evolving landscape of physics, because it's the leading dimension 5 gauge invariant operator that's allowed by the standard model. And since we have, right-handed singlets are absent in a minimal standard model, the transition to Majorana mass terms represents a fundamental shift in our understanding of the U1 invariance of the standard gauge invariance of the standard model. Okay, implying lepton number violation and other things. So this leads to the Majorana mass matrix after electroweak symmetry breaking. And so there's 3 primary ultraviolet realizations of this operator. There's the type 1 realization of this operator called the heavy-handed or heavy right-handed neutrinos. There's the type 2, which, and by the way, these are all what are mathematically kind of enumerated. The type 2 comes from scalar triplets, and then the type 3 gives us fermion triplets of this particular operator. Now, regardless of ultraviolet completion, there's the fundamental experiment in neutrinoless double beta decay stands as the singular, unambiguous experimental signature of Majorana mass. So the necessity to confirm this process, which is primarily like some of the work that I had done like 3 years ago, and I continue to think about this every day, is the theoretical operators to the complex kind of nuclear environment where these decays are sought. There's very, very high experimental errors that need to be tamed. So that's why there's so much effort that's gone into this. Now, the search for neutrinoless double beta decay is basically the search for a process where normally this reaction to conserve lepton number, we should have 2 antineutrinos for, our atomic number and then, everything else. But the detection would prove that the change in the lepton number violation would be equivalent to 2 here. So that means we're missing 2 neutrinos because, for every neutrino that comes out in the weak interaction corresponds, an electron or a positron, right? An neutrino and antineutrino respectively. So the effective Majorana mass from an observed half-life is complicated by significant theoretical uncertainties of the nuclear mass elements. God bless anybody who works on the theoretical side of the nuclear matrix elements in NMEs. So basically you have this phase space factor, and because they're called NMEs systematics, they don't cancel across different nuclei. So you'll have multi-isotope basically strategies that all of these experimentalists have been working on. So that's what the Legend, the Nexo, and Cupid programs are there to ensure that there's any potential discovery and making sure that it's robust against any theoretical dependencies. So that's kind of the this multi-pronged or multi-probed approach to the current benchmark in germanium-based detection. So the current experimental status is that we have 140 kilograms germanium for the results that we. Sorry if I'm cutting out. These are results. Specifically have and an exposure of 61 kilogram years between 2023 and 2024 with the background rate. They combined data from Gerda, Majorana, and all these past experiments to find a limit. They basically place an upper limit on the decay rate, which shows that this is basically an order of magnitude leap that's required to explore the remaining mass ordering space of that neutrino mass, of that nuclear mass matrix element. Okay, so this is specifically what I had some work on, which was the ton scale germanium objective. And by the way, I'm also part of the Legend collaboration. If anybody is interested in inquiring about that, I have some experience as well with this. So yeah, but you can fully probe these inverted ordering regions of the, basically experimentally, we can probe the mathematical landscape of the nuclear matrix element. And this requires a factor of basically 10 improvement in background levels. So that's a goal that dictates every aspect of this detector's design. So we're basically trying to accomplish a ton of enriched germanium-76, and the critical challenge for this is the sensitivity of cosmogenic isotopes. So, like specifically for germanium-68 and cobalt type things. If crystals are grown on the surface, these isotopes could consume about 20% of the background budget. And so Consequently, we prioritize an underground zone that's refining the fabrication at the surf. Surf is another experiment that's happening in like South Dakota at the 800-foot level. So yeah, just there's a bunch of alternative technologies that are trying to provide this like isotopic cross confirmation of any discovery. Now there's the ton scale detectors, so Nexo and Cupid. Xenon time projection chamber, and so basically this time projection chamber, sorry about that. This time projection chamber basically gives us a dual readout for the liquid xenon charge and scintillation readout, and it gives us like a 10-year half-life sensitivity for the double beta decay element, and then also Cupid as well allows us to move away from time projection chambers and use scintillating bolometers at around 10 millikelvin. So that's like near perfect particle discrimination. And there's a Bayesian inclusion target that and this is where the fundamentalists and Bayesian physicists kind of and experimentalists kind of debate, and then I'll leave that to them. But there's a diverse kind of approach to coalesce a sensitivity map that allows us the global reach. This allows us the global reach of the neutrinoless double beta decay program. Okay, so basically, to have a nice comparison between the detectors, we can utilize these standardized metrics across different isotopes, and this gives us the primary reach of the beyond the standard model candidates. So the basically the Legend 200 and then the upgrade to the Legend 1 ton experiment with a complete array inside of liquid argon. Basically, I just want to show you that these nuclear mass matrix elements for the double beta decay are collaboration specific, and they're based on the distinct theoretical models. They're not interchangeable for cross-isotope calculations. So this table is just kind of just showing you how the experiments populate the neutrino mass ordering bands. Okay, and we can kind of map the sensitivity of what this looks like. And this plane, this lightest possible mass with the double beta decay mass, is a critical background for determining the neutrino mass ordering. And this is the strategic design of our next generation experiments that is specifically calibrated to provide definitive answers in this space. So the reach for Nexo and for Legend 200 offer us this deepest reach into the normal ordering region that gives us all of these things. So while we have a lepton scalar sector, it provides a laboratory path to beyond the standard model physics. The strong CP problem provides this also track through the search for the axion. So the axion candidates and the strong CP problem basically comes from the quantum chromodynamics Lagrangian that allows for these violating terms. Yet, even though we allow this CP violating term, the experiment shows that this is not happening, right? The violation is not happening. So this shows us that there could be an axion field that represents this. It's a mathematical solution to this problem because it provides both a mechanism for charge parity restoration with a viable dark matter candidate, and also axion mass and decay constant are linked by the topological susceptibility by the mass of the axion with basically represented in terms of chi. So we must address the quality problem. It's called the quality problem. So you have these Planck suppressed operators of the form of psi n over the Planck mass with basically the field itself that's shifting that axion potential, and it's ruining the ability to solve the CP problem unless these effects are suppressed by a factor of q times 10 to the negative 62, which is extremely it's a very high, a very high suppression. Okay, so or sorry, it's a very strong suppression. That's the word. So basically, this is a theoretical challenge that gives us the rigor required needed for direct dark matter detection. Just kind of showing you this. Okay. Now, the dark matter direct detection at LZ, it's called the Lux-Zeppelin experiment at SURF. I actually had a classmate that worked at SURF. Shout out. I'm going to send her this video. But basically, this represents the world-leading search for weakly interacting massive particles, and LZ utilizes this dual-phase liquid xenon, basically TPC, time projection chamber, which strategically designed to isolate potential weakly interacting massive particle signals from massive backgrounds. I'm gonna butcher the experiments. She'll probably laugh at my drawing here, but yeah. So LZ kind of measures the prompt scintillation and then its drifted charge across electroluminescence, and the ratio of these two signals provides the physical basis for separating electron recoils from gamma and beta backgrounds from the nuclear recoils that basically has the signal that's expected from these weakly interacting particles or neutrons. Okay, and the results from this was actually a world-leading exclusion. So these are very extremely sensitive detectors that have been, they're just a feat of engineering. And the future searches for this are basically to reach something called a neutrino fog, CEVNS, where the solar and the atmospheric neutrinos give us an irreducible background limit. And so this specifically is kind of like why we talk about neutrino observatories now, because we've created these super sensitive time projection chambers that just have extraordinary capability and imaging capability from solar neutrinos and like neutrinos that come from the sun and stuff like that. Okay, so it's called the neutrino fog. So in this local search for dark matter, we also turn to long baseline measurements to further constrain the neutrino sector. Okay. Now there's also the long baseline oscillations at Dune. This is the deep underground neutrino experiment. That sounds very uncreative. Physicists are very uncreative with our naming schemes. But you have a strategic kind of priority for measuring how matter effects influence neutrino oscillations over 130 kilometer baseline from, basically they're going to send neutrinos from Fermilab to SURF. So I'm going to try to detect it. It's pretty creative. You should look at the story behind this experiment. It's pretty beautiful. But the distance is optimized to determine the mass ordering and measure the CP violating phase. Okay. And so that's the ambitious goal of this. It's a beam with 1.2 megawatt beam that's upgradable for higher intensities, and then with liquid argon time projection chamber modules, and then beyond standard oscillations, Dune's high intensity beam allows for these specific searches for sterile neutrinos and non-standard interactions, which might be mathematically interesting and physically interesting as well. So yeah, they're just fundamentally supported by these higher level theoretical frameworks that ensure our models are mathematically consistent. Now, this gets into more of the grand kind of ideas and the grand unified embeddings within the standard model, because these questions start to emerge once we've spent the beginning of this century trying to effectively constrain the standard model and kind of test its boundaries and limits, and we're going to continue to do that for probably the next decades and discover interesting things. So local anomaly cancellation is a prerequisite, and it's not enough. Hold on. All right, sorry about that. The Witten SU2 anomaly demonstrates that there's an odd number of fundamental Weyl fermions, and that an odd number of vial fermions is mathematically inconsistent. So this dictates that the spin 10 grand unified theories are actually the most natural embeddings for the standard model, as they predict a 16-dimensional representation that requires right-handed neutrinos. And furthermore, modern classification via spin cobordisms show that the cancellation of these special classes, require the presence of 3 right-handed neutrinos, or the existence of a hidden gapped topological quantum field theory. The hidden gapped, you can think about this as fractionalized dark sectors. Okay, so this is where it gets really, really interesting. And the requirements to bridge the gap between these abstract, topological programs and these very particles that we seek in neutrinoless double beta decay, and maybe even Majorana modes and Majorana oscillation experiment types of things that appear in condensed matter systems. Even though we're really focusing on fundamental particle physics here, that also kind of opens a can of worms. But these specific oscillation experiments on the fundamental nature of reality, we might possibly have fractionalized dark sectors for a nice topological quantum field theory that will allow us to work through this. Okay. Now, lastly, the spectral standard model and geometry is something I think everybody in the jet space should familiarize themselves with. Alon Khan has a text called Non-Commutative Geometry, and basically it is a mathematically rigorous framework for unifying gravity with the standard model itself. It's one of the many ways to do this. I'll do another talk someday on post-Einsteinian gravitation, but in the spectral standard model, this is a very promising candidate for a way of thinking about this. The universe is actually just described by a spectral triple, and the Higgs field actually emerges as the internal kind of component of this geometric connection. So geometric unification would look like saying we have a spectral action that naturally yields the Einstein-Hilbert and Yang-Mills terms, and then the Majorana connection. This is a critical prediction of the framework, which is that there could be an existence of Majorana right-handed neutrino masses that force a dimension of 6 on the finite KO dimension of 6 on the finite space. So it becomes kind of a you have to start a finite algebra and then show that you can then have a total dimensionality of 10 with 4 plus 6, that then provides a geometric justification for the low energy Majorana mass terms that we actually are producing experimentally. That would be a very interesting and surprising kind of explanation for this tension that we have in low energy cosmology. Now, lastly, is the big cosmic discrepancy that's been here for a while, is the Hubble tension. So it's a greater than 5 sigma discrepancy between the early and the late universe measurements of the Hubble parameter, which comes from our Friedman, Lemaitre, Robertson, Walker metrics. And if you need a reference, go to Landau 2, Landau Volume 2, last chapter. Okay, but this discrepancy suggests that the fundamental lambda CDM model is an incomplete description of the expansion history of the universe. So you have Planck, the early universe, that's model independent. You also have late universe things that are becoming model dependent. So also the recent JWST observations, James Webb Space Telescope observations, have confirmed the HST SIFID data. So that excludes that stellar crowding as a source of error at the 8 sigma level, which is pretty interesting. So this cements the Hubble tension experimentally as a genuine physical discrepancy rather than some kind of experimental artifact or anything like that. Okay, so the next decade of discovery. This is something that keeps me up at night, keeps me doing these little lectures at it's like 4 a.m. here. And thank you guys for being here. But this next decade is going to represent an experimental squeeze on the standard model. And we're entering this nice territory where the primary failure modes of the standard model, where we have neutrino mass, dark matter, and cosmic expansion, they're all going to be subjected to unprecedented experimental pressure with the engineering and technology that we've built. These massive radio pure apparatuses that are just just some of the best in the world. Okay, so basically the discovery standard for this era is pretty absolute. We have multi-isotopes, multi-technology confirmation, and those things are mandatory. So not a single isotope or detector technology will be sufficient to claim an entire paradigm shift. We have to do it all around to make sure that we get interesting violations of the low energy limit of the standard model. So, Legend 1000, Nexo, and Cupid are the ones that I would look out for these next decades and be excited about, because they're supposed to provide full coverage of the inverted ordering and enter the normal ordering regime. LZ and XLZD, these are the other experiments. They are pushing the WIMP hypothesis to its ultimate limit and at the neutrino fog itself, so that we can basically have this imaging stellar observatory kind of thing that's happening with the neutrino detectors themselves that are like underground in Earth, just absolutely radio pure. And then there's the Dune experiment that's going to provide the definitive measurements of the CP violation and mass ordering. Okay, or CP invariance. Okay, so we're moving from this idea of exclusion to now physics is at this threshold, if you will, of discovery. We're going to enter an era of new physics, whether people realize it or not. We just have to be creative about the data that we are given and the mathematics that we're given as well. So the territory that we have really defines the next century of fundamental physics. So here's the references. If you guys are rewatching, etc., all of the citations and everything, or if you want to look more at this, I've concisely put citations here. There's the first page of the reference. There's the second page of the reference, and that's all I have for you guys today. Are there any questions? I just wanted to open up the board. I would have to look back at the book. Man, I've been going on a crazy rabbit hole, but the spectral triple is essentially a Hilbert space, something, a Dirac operator. That's what D is, and I think an affine group. I have to double check. But the A thing is the thing that I don't know. But it's basically the spectral triple in the non-commutative geometry sense is essentially what we're basically replacing the manifold itself, and this trace here is actually this trace of the chi. I think it's suppression or something like that. Is the action. So this is called the spectral action, and you have this Dirac operator, and then the spectral action itself, where you take the Dirac operator quotiented by lambda, which has other kinds of terms and stuff. It's really complicated, but that's basically what the spectral triple is. It's in Alain Kahn's non-commutative geometry book that I'm referencing this from. Any other?
In Hilbert space, and then
sorry. Yeah, of course. Yeah, this is definitely one of the most exciting things in my opinion. Sorry, I cut out. But this is definitely one of the most exciting things, in my opinion, is the spectral action and the spectral triple and the endeavors in non-commutative geometry for doing physics beyond the standard model. This is kind of the floodgates that have opened pretty much. So yeah, are there any other questions? Honestly, if you look at any of these collaborations, any of these papers, the people who have created these experimental apparatuses, you will see that there's really no single physicist. It's just been a massive experimental effort, and these papers have like so many people cited on them, like entire like it's just so much. Like I could cite my mentor, like that's how much it of a group effort that it's been to get the experimental tests of the standard model in general. In terms of things to look out for, I would look out for on the theory landscape. I would look out for uh, Nima Arkhani Hamed, of course, Sabrina Pastursky in celestial holography. I had the pleasure to actually meet her. She's awesome. And yeah, I mean, just people like doing the celestial holography initiative. I think that's a really interesting physical direction to go. Alon Khan is actually a mathematician that I would definitely just study his work, just study his life's work on the standard model specifically. And yeah, that's all I have for now. I will compile a list maybe in the future in directions that I think are interesting. Also, you guys find interesting directions as well, which are cool. So, yeah, that's my answer to your question. Are there any other questions? Well, it was a blast. Oh, yeah. Uh huh. Oh, yeah, yeah. Is it here? Um, Let me see. Yeah, I forgot. Oh, actually, I think it was right here. Yeah, yeah, swamp. Oh no, this is the swamplands. Yeah. Uh huh. Yeah. So the swamplands basically merge both mathematical and physical kind of language. So it's kind of put everything together. But the oh, sorry. Can you hear me? Hello. Okay, perfect. So yeah, it's kind of a mix of a bunch of terminology between mathematics and physics. Um, in terms of the basically, there's specific anomalies that get excluded from the swamplands, or kind of the swamplands conjecture is kind of the space of it's something that you can completely add, or it's like a space that you add a bunch of like unphysical theories to, like, that don't have any kind of effect effectively, if that makes sense, for the standard model, or like their anomalies don't like cancel or whatever. And so the cobordism, or there's a cobordism conjecture, and there's also spin cobordisms that come from mathematically these. It's something called atom spectral sequence or whatever. And these kind of like, I guess, how you have to. So they're cancellations of. Uh huh. Oh, go ahead. Yeah. Mm. I'll definitely have to. I'll have to read. I'll have to review that. That might have been a mistake on my end. Hello. Okay, I was just gonna say I'm gonna have to review that because that might have been a mistake on my end. Um, yeah. Um, if the give us the spin coordinates.
I don't.
Yeah, I'll have to double check that. Um, we shall see. We shall see. Time will tell. Was there anything else, by the way? Anybody else had anything to comment on? Feel free to pick apart anything. I don't know how many experimentalists there are, but I'm sure this was a little bit embarrassing for the experimentalists. Secondhand embarrassment. Okay. Well, if there is nothing else, this video will be on YouTube probably tomorrow-ish. It is currently 4 a.m. where I'm at, so it's been a pleasure talking to you guys, and let me know if there's anything else that I can do. I'll have these slides also available for people in the Discord to look through, and it'll be in a GitHub repository. Okay. Thank you guys so much, and I'll see you guys next time. All right.